Good day, I'm Norman Wahlberger. Today we're going to carry on with this little series on a bunch of related topics. Last time we talked about relativistic velocity addition, Einstein's special theory of relativity, and the connection with projective one-dimensional geometry. Today we're going to talk about a new kind of circle we're going to identify, which we're going to call a core circle. And in our next video, we'll talk a little bit about Paul Miller's protractor and then tie these various things together. Alright, so circles is something that we have talked about earlier in this series. I hope you remember some of those videos. In particular, we defined a circle to be a symbol, something like this, which is specified by a point, AB, and a number, K. And to this symbol, we can associate this equation, x minus a squared plus y minus b squared equals k, which we recognize as a circle with center AB and quadrants k. Not radius, but quadrants. Okay, there are three really important circles. And we've talked about two of them. We've talked about the unit circle, which has equation x squared plus y squared equals 1. Plays a very important, prominent role in all this geometry, centered at the origin, quadrants equal to 1. At some point I've also mentioned this imaginary unit circle with equation x squared plus y squared equals minus 1. And you probably were wondering why I call that the second most important circle. We are still in the process of finding that out. That will be revealed a little bit later. But today I want to talk about a third kind of really fundamental, important circle, which I'm going to give this name core circle. So the core circle is the circle with center 1/2, 0, and quadrants 1/4. And its equation is x squared plus y squared equals x. So a lot like the unit circle, but there's an x on the right-hand side instead of a 1. So we're going to be looking at this circle today, and it turns out that it's very interesting for us, and we get to see certain things more clearly when we look at this core circle rather than the unit circle. Alright, so these various things have extensions and generalizations in other metrical geometries. In particular, if we're working in the relativistic red setting, we can also inquire about analogs of these things, and we'll see that they play a role too. So let's begin by reviewing some essential facts about our unit circle, the circle with equation x squared plus y squared equals 1. And then we'll look to sort of modifying some of these facts for this core circle. Alright, so here's our unit circle in the xy plane, diameter going from -1 to 1. One of the very fundamental things about it, which I emphasize many times in my channel, okay, a very fundamental fact that all undergraduates should well know, is a rational parametrization of this thing. And that can be thought of as arising from choosing a point on the y-axis with coordinate t, joining the point -1 here on the x-axis to that point t, and seeing where that line meets the circle in the other point. We call that E of t, then a little calculation shows that's 1 minus t squared over 1 plus t squared and 2t over 1 plus t squared. So I hope you've all memorized this formula by now. A few videos ago, we looked to generalizing this a little bit because this is a little bit imperfect in that this particular point here plays a sort of a singular role with respect to this parametrization. It corresponds to t equals infinity, which is maybe a little bit nebulous. So the way to overcome that difficulty is to move to a slightly more general projective parametrization, which brings out the importance of the projective line again. Now what we're going to do is we're going to parametrize the same circle by a projective one point, u to t, and here's the formula. U squared minus t squared over u squared plus t squared 2ut over u squared plus t squared. When u equals 1, then we recover the earlier rational parametrization. Now this can also be described in terms of complex numbers conveniently. it can be thought of, if you think of a complex number as a pair, like this, as the complex number u plus it divided by u minus it, the complex conjugate. And another way of writing that is to think about it as being the complex number u plus it squared divided by the quadrants of that complex number, which is just the sum of the squares of the real and the imaginary parts. In other words, u squared plus t squared. Okay, and with regard to this rational parametrization, let's just make a few other observations. That if we look at the line through the origin, which is parallel to this line here that we use to construct our point E, then this line here passes through this point 1t, because it's just shifted over by 1 in the x direction. So its slope is t, and it turns out then that another way of thinking about this point is as the reflection of the point 1 in this line here. Okay, so now the connection with projective quadrants or spread. This line and this line are two projective 1 points. If we just think about our one-dimensional projective situation, then lines to the origin, exactly what we're talking about, and the relationship between these two lines is determined by a projective quadrants. Now in this case, the projective quadrants between this line and this line is t squared over 1 plus t squared. Remember, this is the line 1 to 0. And if you use the standard formula, 1 times 0 minus 1 times t, all squared, over 1 squared plus t squared times 1 squared plus 0 squared. Then you'll get t squared over 1 plus t squared. So that's what we usually call a projective quadrants. But in this two-dimensional setting, when we're talking about planar geometry, I like to use the word spread instead of projective quadrants. Projective quadrants is something that's really sitting in the projective world, while spread is a purely affine quantity. Although they happen to agree here. They're exactly the same. So we can define the spread between these two lines as being the projective quadrants in the usual fashion. So this quantity, t squared over 1 plus t squared, we recognize this is the quadrants of this opposite side in this little right triangle divided by the hypotenuse quadrants. So it's really like a square of a sine of an angle if you believe in angles and if you believe in things called sines. So this connects with trigonometric stuff quite naturally, but the point is that this quantity is purely algebraic and requires no infinite processes. Alright, so please check this formula, and you can check that this projective quadrants and this projective quadrants are in fact the same. It is actually true that this is what the bisector between these two things here, which reinforces a familiar fact that in classical geometry is referred to as saying that the angle subtended by a chord at the center is twice the angle subtended at a point on the circumference. So in terms of angles, this would be twice the angle of this. But we're going to see very clearly that we don't want to think in terms of angles. It's much preferable to think in terms of spreads. Everything becomes much clearer and ultimately more logical and tight. Alright, so this is a quick review of hopefully things that you've become very familiar with regard to the unit circle. Now we want to change gears a little bit and look at this core circle from roughly the same kind of point of view. Alright, so the core circle is defined by having this equation. It has center, the point 1/2, 0, and quadrants 1/2 squared, or 1/4. If we expand this thing out, we're going to get x squared minus x plus 1/4 plus y squared equals 1/4. And then the 1/4s will cancel. If we bring the minus x to the other side, we'll just have x squared plus y squared equals x. So that's the same equation. The center of this circle is the point 1/2, 0. There's the circle right there. It passes through the point 0, 0. It also passes through the point 1, 0, because 1 squared plus 0 squared equals 1. The quadrance of this thing is 1/4, the right-hand side there. The radius would be 1/2, but we prefer to think in terms of the quadrance, so that's 1/2 squared or 1/4. This thing has a diameter, which is the interval from 0 to 1. It has the property that it's symmetric about the x-axis, because if you replace y with minus y, then you still get another point on the circle. So there's a diameter right along there, and this distinguishes it from the unit circle, which is this one here, which has diameter from -1 to 1. We'll see later in this course that in many ways the interval 0, 1 is more important and fundamental than -1, 1. So this is going to be a theme which will gradually become more and more important as we go on. We're going to see that, yes, the interval -1, 1 is a very important interval in mathematics. But for many purposes, the interval 0, 1 is actually more basic and more fundamental. I just want to plant that idea in your mind, so let it resonate there for a few months or perhaps years, and eventually you'll come to appreciate this. So the three numbers 0, 1, and -1 are the three most important numbers in mathematics. Right, for sure. They are the three most important. And if you had to say which of these three are the most important, you'd have to say that 0 and 1 are more important than -1. Just the way things are arithmetically. Right. So these two numbers are a little bit more important than -1. That doesn't prove anything, but it's suggestive that perhaps this interval 0, 1 actually really is more important than the interval -1 to 1. Which would be then followed by the idea that, okay, maybe this circle, which is built on the interval 0, 1, deserves at least as much attention as our much more familiar unit circle that we're always drawing. One of the things I'd like to promote in this series is a kind of a flexibility. The idea that we don't have to be wedded to one particular point of view. That we're prepared to change our orientation and look at things from a different point of view, adopt new possibilities, and venture forth towards new horizons. This is a small such step to regard this interval 0, 1 as really a lovely interval. We'll see later on that that has a lot of repercussions. A lot of repercussions to that little observation. So there's our new core circle with the equation x squared plus y squared equals x, sitting inside the unit circle. And now we want to study that core circle a little bit more carefully. So one very noticeable advantage to this core circle is that it has a more direct relation to the projective line P1 that we've been talking a lot about. Because if we visualize our projective line as lines through the origin here, then the origin happens to be a point on the circle rather than the center of the circle. That makes a big difference in terms of the way the projective line of these one-dimensional subspaces of our affine plane interact with the circle. So we can see that by asking the following question. Where does this particular line, the line u to t, so here's a point u comma t in the affine plane, and here's a line through that point and the origin. This is the line that we would usually call the projective one point u to t. It's determined by the proportion between these two numbers. So let's call it A. And the question is, where does this line meet our core circle C? So this line, as a line in the two-dimensional space, can be viewed as multiples of this point, or probably better yet, this vector. Or there's the equation of the line if we wanted to write it as an equation in x and y. So how are we going to find this point here? Well, we're just going to take the point lambda u t and plug it into the equation of the circle and solve for lambda. So if we put lambda u in for x and lambda t in for y, we get lambda u squared plus lambda t squared equals lambda u. Bring everything to one side and factor out the common lambda. We get remaining lambda u squared plus lambda t squared minus u equals 0. So if a product of two things equals 0, then either lambda equals 0, in which case we're just talking about the origin 0, 0, which we know is in fact, yes, a solution to the meet of the line and the circle. Or, more interestingly, this term being 0 means that we can solve for lambda in terms of u and t. We get lambda equals u over u squared plus t squared. In other words, the x-coordinate of the point we're starting with divided by the quadrance of this point, at least from the origin. And so if we look at lambda times this point, multiply the coordinates u and t by this lambda, then we get what we might call c u to t, which is u squared over u squared plus t squared, and ut over u squared plus t squared. So this is a parametrization of the circle. It's a parametrization which is a projective parametrization, very much in keeping or in the same direction as our projective parametrization E of the unit circle. You can see it's a little bit simpler than that other one. It's quite similar. There's a u squared plus t squared in the denominator, as there was in the other example. But for the unit circle, we had a u squared minus t squared, and we had a 2ut. So this is marginally a little bit simpler. But geometrically, it's simpler because we haven't had to move from the line. We've taken the line and we've just scaled, found a convenient point on that line to identify with the point on the circle. That's not what we did with the unit circle story. We had to square that complex number, which took us off the line that we were interested in, and then scale that thing down. Now there's an interesting alternate approach to get at this parametrization of our core circle, which is to look at our unit circle and take the parametrization that we have of that and just dilate the circle by a factor of 1/2 and then translate it over again by 1/2. That's how geometrically we can go from the unit circle. If we dilate by 1/2, then we get a circle here which has quadrance 1/4 or radius 1/2, which is the same as our core circle. It's just that it's centered now at 0, 0 instead of at 1/2, 0. So if we then subsequently move it over by 1/2, then we're just at the core circle. Okay, so we could take the point that we know, e u to t, which is u squared minus t squared over u squared plus t squared, 2ut over u squared plus t squared, and see what happens to that point if we dilate by a factor of 1/2 and add 1/2. So if we dilate by 1/2, the first thing that happens is that we have to divide here by 2, and this 2 factor here disappears. And then next we want to move over by 1/2 in the x direction, which just means adding 1/2 in the x direction. So what do we get when we do that? Well, this is just the same as that. Here, when we put everything over a common denominator, there's a 2u squared plus t squared. If we multiply top and bottom here by u squared plus t squared, then the u squared minus t squared plus the u squared plus t squared will give us 2u squared. The 2 will then cancel with the 2 that's on the bottom, and we'll just get u squared over u squared plus t squared. So we're going to get exactly the same story that we got in the previous slide, what we call c u to t. So this is sort of interesting that our same line, u to t, which generates the parametrization for our unit circle by essentially multiplying this complex number by itself and then dividing by its quadrants, that really is effectively the same as normalizing, just dividing this thing by that lambda factor to get on our core circle. All right, so here I've just sort of summarized that projective parametrization of our core circle. There's our formula for it, which is actually a multiple of u and t, that point there. So now I want to go back to an interesting theorem that we established for the unit circle, with the idea of getting the corresponding theorem for the core circle. This is the unit circle quadrance theorem, and it was derived in Math Foundations 129. You might want to have a review of that. It told us that if we have 2 points, E1 and E2, on the unit circle, whose projective parameters were U1 to T1 and U2 to T2, then the quadrants between those 2 points, and we're talking about capital Q, that means affine quadrants, change in x squared plus change in y squared, that kind of affine quadrants, that was equal to this following expression involving the 4 numbers u1, t1, u2, t2. 4 u1 t2 minus u2 t1 squared over u1 squared plus t1 squared, u2 squared plus t2 squared. Now at the time, I remarked that this was quite an important expression, and now you've had a lot more familiarity with projective quadrants, so you don't need any more convincing. You know that yes, this is a very important quantity. This is basically the replacement for an angle once you start doing planar geometry or even one-dimensional geometry correctly. However, there is a factor 4 here. That factor 4 did not figure in the projective story. All right, so now let's look at the corresponding fact for the core circle, the core circle quadrance theorem. It is that if we have 2 points, C1 and C2, on the core circle, in other words, they're parametrized by C of U1 to T1 and CU2 to T2, then the ordinary Euclidean quadrants between those 2 points on the core circle is given by exactly the same expression, but without the 4. And now we can say, well, that is exactly the projective quadrants between these corresponding projective 1 points, between the 1 point U1 to T1 and the 1 point U2 to T2. We get an exact correspondence between the Euclidean quadrants between 2 affine points and the projective quadrants between 2 projective 1 points. This really is demonstrating that yes, there is a lovely connection between the projective line and this core circle. This will be a major tool for us. All right, so let me demonstrate this lovely fact in an explicit example. And as usual, I'm prepared to give you explicit examples for which we can actually demonstrate the truth of our theorems by making explicit calculations which we can actually finish. We don't have to point and say, oh, well, if we kept on doing it, we would get this. No, we're actually going to make the calculations, and we're going to see that the left-hand side actually equals the right-hand side without any 3 dots. Okay, this is a 3 dotless theory here. I'm interested in 3 dotless mathematics. All right, we're going to choose 3 projective 1 points, very familiar ones. The 1 point 1 to 2, which we'll call A1. The 1 point 3 to 1, which we'll call A2, and the 1 point minus 1 to 1, which we'll call A3. Corresponding to each of those are the corresponding points on our core circle. A1, A2, A3. How do we get A1? We get A1 by taking the point 1, 2 and multiplying both coordinates by the number lambda, which is the x-coordinate divided by the quadrants. Quadrants being 1 squared plus 2 squared, or 5. So we're going to multiply both entries by 1/5 to give us 1/5, 2/5. That's that point there. The point A2 is obtained by taking 3 to 1 and dividing both entries by the product of the x, which is 3, divided by the quadrants, which is 9 plus 1, or 10. So we multiply both by 3/10 to give us 9/10 and 3/10. That's that point there. And the point A3, obtained by taking minus 1, 1 and multiplying both entries by minus 1 over 2. 2 because it's 1 squared plus 1 squared. To give us 1/2 minus 1/2. And that's the point A3 down there. Now, the projective quadrances formed by these three lines, something that we've had a look at. We've computed before that the quadrants between 1, 2 and 3, 1 is 1/2. That the quadrants between minus 1, 1 and 1, 2 is 9/10. And the quadrants between minus 1, 1 and 3 to 1 is 4/5. And we can denote these quadrances here on our diagram by little lines. It's the same notation that we use when we're talking about spreads. So we don't get confused with angles, because we're not talking about angles here. We don't want to talk about angles. We want to talk about the spreads or the projective quadrances. These are the really algebraic, essential aspects of things. So there's a spread or projective quadrants of 1/2 there, 4/5 there, 9/10 there. Now, what did we just assert in that last theorem? We asserted that these projective quadrances correspond to the affine quadrances between these corresponding 3 points. If we calculate the affine quadrants, capital Q, between A1 and A2, so difference in x coordinates squared plus difference in y coordinates squared, there they are there. So 9/10 minus 1/5 all squared plus 3/10 minus 2/5 all squared. So that's 7/10 squared, that's 49 hundredths. And that's 1/10 squared, that's 1/100th, for a total of 50 hundredths, or 1/2. And similarly, the quadrants between A2 and A3, you can check that sum of squares is 4/5. And the quadrants between A1 and A3, that sum of squares is 9/10. So absolutely direct connection between the geometry of our one-dimensional projective setting and this affine geometry in the plane, where we're looking at points on our core circle. The quadrants between these 2 points is exactly the same as the spread between those 2 lines. That half and that half are the same. The quadrants here is exactly the same as that spread there, or projective quadrants, 4/5. And that quadrants there, 9/10, is the same as that spread or projective quadrants between these 2 lines. And our notation is that if there's not enough room, we can put the little line anywhere between the 2 lines. So between this line and this line, we could put it there, or we could put it there, we could put it there, or there. That 9/10 equals that 9/10, that 1/2 equals that 1/2, that 4/5 equals that 4/5. So we're connecting in the most direct possible fashion our understanding of one-dimensional projective geometry with the regular affine Euclidean geometry of the plane. And the intermediary is our core circle. That's sort of the link between these 2 things. Okay, so your exercise is to prove the core circle quadrants theorem. And there's an easier way to do this, and there's a slightly more involved way of doing this. The easy way is to take the corresponding result for the unit circle and just see what happens when you dilate by a half and translate by a half. The more elaborate way is to go back to the fundamentals and make a computation. So either way, prove the core circle quadrance theorem. Alright, now I want to turn to another important result that we established in Math Foundations 129 for the unit circle. I want to see what the analog is for our core circle. This was the unit circle signed area theorem, which told us what the signed area is of a triangle formed by 3 points on the unit circle. So if E1, E2, E3 are 3 points on the unit circle with rational parametrizations in the obvious ways, then here was an expression for the signed area of the oriented or signed triangle E1, E2, E3. And that might have looked rather complicated back then, but now you probably look at this in a new light, I hope, and look at that and say, wow, I kind of see some projective quadrances there. I didn't before, but now I do. In fact, it looks like there's almost 3 projective quadrances. At least there would be if we square this whole thing. Well, actually squaring things is what we want to do anyway, because the signed area depends on the orientation of our triangle. Remember, if we go this way or if we go this way, the signed area changes by a factor of -1. If we want something that's independent of orientation, we want to square the signed area. And we've seen that for various reasons. If we square the signed area and multiply by 16, then we get the true quantity, which is called the quadrea. All right, so 16 times the square of this is really the fundamental sort of area kind of measurement associated to a triangle. Right, so now to the core circle. The core circle quadrea theorem. We have 3 points on the core circle, C1, C2, C3, given by parameterizations just as before, U1, T1, U2, T2, U3, T3. Then the theorem is that the quadrea of this triangle, C1, C2, C3, which I remind you is 16 times the square of the area, is 4 times Q1 times Q2 times Q3, where Q1 is the projective quadrance between this projective 1 point and this projective 1 point. And Q2 is the corresponding one between these, and Q3 is the projective quadrance between this one and this one. So your exercise, use star to prove this. We know geometrically how to go from our unit circle to our core circle. You divide by 2, dilate by a factor of half, and then translate by a half. Those are very simple operations. We can figure out what that does to signed areas. So knowing this for the unit circle, we can establish this very pleasantly and simply for the core circle. Let's have a look at an example. All right, so our example will be exactly the same triangle that we were looking at before. A1, A2, A3 with coordinates 1/5, 2/5, 9/10, 3/10, and 1/2 minus 1/2. This triangle sitting inside our core circle, what's its quadrea? Well, the quadrea is 16 times the square of the area. So you could use a determinant to calculate the area because we know the coordinates of the points. But we also know the triple quad formula. We know Archimedes' formula for the quadrea. It's Archimedes' function applied to these 3 quadrances, 1/2, 4/5, and 9/10. So 4/5 plus 9/10 plus 1/2 squared minus 2 times the sum 4/5 squared plus 9/10 squared plus 1/2 squared. Basically our rational analog of Heron's formula. And then you compute this, and you find out that you get 36 over 25. So that's 16 times the square of the area of that triangle. Of course, you can use that to calculate the area very quickly if you want to. But this same number also equals 4 times the product, 4/5 times 9/10 times 1/2. That product also evaluates to 36 over 25. And that's what the theorem asserted. The theorem asserted that the quadrea of this triangle was 4 times the product of these 3 projective quadrances. And I want to restate this in a way that's sort of independent of spreads or projective quadrances, purely as a Euclidean theorem. We'll call it the core circle triangle quadrance theorem, which is that if Q1, Q2, and Q3 are the quadrances of a triangle in the core circle, like this one, then Archimedes' function applied to Q1, Q2, Q3 equals 4 times Q1, Q2, Q3. Exactly the situation that we have here. This is the quadrea of the triangle. This is 4 times the product of the quadrances. These are going to be equal if our triangle is inscribed in the core circle. The actual points are lying on the core circle. Now, this is just basically the projective triple quad formula. This is the projective triple quad formula. We can rewrite this by saying this is S of Q1, Q2, Q3 equals 0. Let me note very carefully that just because this relation holds for the core circle does not mean that it holds for a general circle. If you expand our circle by dilating it by a certain factor, the non-homogeneity of this thing will mean that the relation will alter. This is quadratic in the Q's. This is cubic in the Q's. So a dilation is not going to preserve this relation. That is also a statement that has a lot of consequences, as it turns out. So very rich situation, this core circle, and it really does connect very strongly with our one-dimensional projective geometry. In fact, gives us a way of visualizing or interpreting projective quadrants. Instead of asking, well, what's the meaning of the projective quadrants of a half there, we can say, what it really means is that the corresponding 2 points on our core circle are separated by a regular Euclidean affine quadrants of a half. It's another way of thinking about what the spread or the projective quadrants means. In the next video, following on from this one, we're going to see that there's in fact an even more elementary connection between these projective quadrances and this core circle. That was an observation made by Paul Miller. And so we're going to have a look at his protractor, and then we're going to tie the whole story together by noting that things generalize. We can generalize this to a relativistic setting, and then we get connections again with special relativity. Very interesting stuff. So I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.